Hello, in this lesson, I would like to talk about limit laws. We have just talked about the intuitive definition of limit, definition of one-sided limit, and the relationship between limit and one-sided limit. And also, of course, we talk about intuitive definition of infinite limit, definition of infinite limit to cases. And number 6, we talk about vertical asymptote. Okay, after these, based on all of these, we're going to talk about the laws of limit. The laws of limit, we have many items. The first item is about addition, subtraction, multiplication, division, and a constant multiply functions and the various other situations. Let's start from the first one. The first and foremost, what is the premise, right? Under what condition we can apply limit law? The condition is first, under the condition that the limit, the individual limit exists. Okay, so we suppose, suppose, hold on. Oh, I need to change the mode. Suppose following two limit exists. Limit as x approaching a, f of x and the limit of g of x. These two limits both exist. Both exist. Okay? So this is the premise. This is the condition before we can apply the laws of limit. Then, so we're going to explain what that means. Okay? Then the limit of sum f of x plus g of x is equal to the limit of f of x plus the limit of g of x. In other words, the limit of sum is the same as the sum of limits, provided that both limit exists individually. Now, the second property is under the same condition, limit of difference is the difference of limit. So the limit of difference is the difference of limit. Okay, so the limit of difference is the difference of limit. Okay, under the same condition. Number 3 is that the limit of product, right? The limit of the product becomes multiplication, is the product of limit if the individual limit exists. Okay, so we must understand the limit of product is the product of limits. And number 4, quotient. So the limit of quotient. So when we divide two limit, right? F of x divided by g of x. We have additional domain requirement. We have additional domain requirement. And with the domain requirement, okay, domain requirement would be the denominator cannot be 0. So in addition to two conditions, the two individual limit exist, we also assume, okay, we also need to guarantee the limit of g cannot be 0. Cannot be 0. If this is satisfied, right? The individual limit exists and will guarantee the denominator is not 0. And then the limit of quotient is the quotient of limits. Okay, so the quotient of limits. So we divide these two limits which both exist. So this is a limit law. And number 5 is also very useful, but it only requires one of the limit exists. So provided that this limit exists and we multiply arbitrarily a constant, and this limit would equal to the constant multiply the limit. So here, so let me put the narrative here, the limit of quotient, Quotient, okay, is a quotient of limit, provided both limit exists. All right, so this is the first 5 properties. We have more, but before we go on with other properties, we'd like to look at some examples. Example number 1. Okay, example number 1. Suppose we have two limits, right? So we have limit f of x. So we've done some examples, right? So one of these examples would be the limit of say x is approaching 0 and sine x divided by x, right? This is the f of x, the limit of f of x, right? So the limit of g of x, say that's equal to sorry, that function, that one is 1 over x. For example, okay, what does that equal to? No, this doesn't exist actually. Let me make up an example. This is going to be x. This is going to be x squared minus x. Okay, so we have two functions. These two functions, before we assess their addition, subtraction, multiplication, division, we have to guarantee that each limit exists. And this limit certainly exists. Okay, we've done that if the limit equals 1. How about this other limit? This other limit, okay, what we can do is that we look at the graph of the function. The graph of the function is, we can graph it. All right. Right here. we have other tools. We have other algebraic tools, but we're not going to use it because we're going to, we will use it in the future. But this time, once x is approaching 0, this function you can see is not defined at 0, right? 0, x is a denominator, so it's not defined as 0. So we cannot plug in. But as x approaching 0, it looks like there is a limit. There is a limit, and that limit is -1. Okay, and in fact, algebraically, we can also demonstrate this limit is equal to -1 by factoring this rational expression. The numerator will be factored into x times x minus 1. By limit definition, as x approaching 0, x is not 0. X is not 0 because we do all these, approaches in the domain. Because x is not 0, x and x can be reduced. So this piece, the next step, the limit will equal to x and x reduced. We got x minus 1. And by this time, we can actually plug in. We're going to learn direct substitution in this case. So that's going to be 0 minus 1 equals to -1. So by this time, we have demonstrated that both limits exist. Okay, so this must be demonstrated or must be confirmed before we can apply all of these limit laws. So next, we're going to apply these limit laws. Okay, so how do we apply these limit laws? For example, okay, I did a copy and paste because in our particular example, right, we don't need all of these. So now in the case of x equal a is 0, f of x is sine x over x, g of x, right? So these two, the limit of sum is sum of limits. So we can just plug in, right, as x approaching 0. And this is sine x divided by x. So it's just a direct application of the limit law. So that's going to be equal to 1 plus -1 and equals to a 0, right? And the second case, the limit of difference, the subtraction will work, right? And that's going to be 1 subtracting -1, and that's going to be equals to 2. And thirdly, multiplication, multiplying, it works, right? Multiply, so that's going to be equals to 1 times -1 and equals to -1. Division, right? We can actually remove these accessories. Okay, you understand these wordings. Division, when x is approaching 0, sine x over x divided by x squared minus x, that's going to be equals to 1 over -1, and the answer is equal to -1. And this piece certainly is guaranteed. right? So this limit not equals to 0 is guaranteed because it is equal to -1, right? So that's guaranteed. So the limit, so we don't even need to mention that. Last but not least, if I choose number 7, right? X is approaching 0, and number 7 multiply the limit of sine x over x, it is just going to be equal to 7 multiply this limit, and that equals to 7 times 1 equals to 7. So you can see applying limit law is pretty straightforward, but first thing first, before you apply limit law, you must guarantee each individual limit exists. Okay, each individual limit exists. So now let's look at another case. All right, let's see. After the fifth property, let's look at number 6. Number 6 is called the power law. Power law. But we still assume that this limit exists. Okay, both limit exist, but we only use one. So the limiting use will have to exist. So under this condition, okay, limit of as x approaching a, and we're going to take a certain power of f of x raised to a power of n. If this limit exists, and that limit is going to be equal to the limit to the power of n. Let me use a proper to the power, to the power of n. Okay, or since this bracket is unnecessary, so we can use a bracket and write it this way. So if the limit of f of x as x approaching a exists, that's the power law. Second, this one is not hard to find examples. And the next one is about the root law. The root law will include, we'll have to consider even number root or odd number root, okay? Still provided that the limit exists, okay? And the function is being taken nth root. So f of x is being taken nth root. If the nth root is even, right, then f of x has to be in the domain of the nth root, the even number roots, which is greater than or equal to 0. So in that case, right, for odd number root, right, so it's going to be the nth root, the limit of f of x after. So the difference between these two is the one is taking limit after the nth root, the other one is taking nth root after the limit. Okay, and we have a distinction to make here. Okay, if n is even, if n is even, we have to assume that the limit of f of x is going to be positive. Well, equals to 0 is fine too, greater than or equals to 0. So odd number root, no worries, right? 8 it's a constant, right? So if we take limit of a constant, and this is just a constant, and the limit is going to be the same constant. And if we take limit of, this is actually, if it's x, right? It's a linear function, right? It's just equals to a. And number 10, 10th law, the 10th law, saying if we are taking x raised to the power n. So this is actually addressing the various cases of polynomial. This is going to be a raised to the power n. You can see in all of these cases, in these two cases, it's just direct substitution. It's just direct substitution. Number 11 is that we're taking nth root of the x. Okay, so this is the nth root of x. The nth root of x. And it is just direct substitution. So this set the stage for the next direct substitution property. Okay, so direct substitution property. This is a very useful property. We actually used it once earlier, right? We used it over here. We used it over here. All right, direct substitution property says if the function f is a polynomial or a rational function, and A is in its domain, in the domain of f. Okay, that's the condition, premise. Then the limit of, I'm going to need that form. Provided f is a polynomial or a rational function and a is in the domain, we can simply directly substitute. In the case we did earlier, right? This function, obviously 0 is in its domain for x minus 1, right? And then we can directly substitute. Then you say, how about the other one, right? So the next theorem will answer that question. The next theorem will answer that question. Next theorem says, if f of x equals to g of x, when x is not equals to a, okay? Think about that. What are the cases, right? So the case we have here is that situation. Now, if f of x equals g of x, when x is not a, in other words, f and g are the same for all the other x's, as long as the x is not a, then the limit is equal to g of x, because they're only different by 1 point. So we're going to illustrate that. Okay, of course, we provided the limit exists. Example, okay, I like to illustrate this. In the case of this limit and the other limit, okay, example, when we consider these two limits, when we consider this two limits, we have two functions here. First function is f of x. Okay, I'm going to call this f of x. Okay, and the other one is g of x equals to x minus 1. The former, the domain of the first one is x cannot be 0. X cannot be 0. The latter, the domain is x is all real numbers. X is all real numbers from negative infinity to positive infinity. Right? So, but these two functions are equal as long as x is not 0. How do we know that? Okay, f of x, we work with this function, right? So f of x, right? So f of x is this piece. We work it in its domain and we factor it, right? We factor it, so x multiply x minus 1 and over x. Because we work this in the domain of f of x is not 0. So for two x, one is on the top, one in the bottom, they're not 0, we can reduce them. We ended up with x minus 1. But x minus 1 as a function alone has a different domain. So these two functions is the same at all points but 1, x equals 0. So this is the case that f of x equals to g of x when x is not 0. So so that is, right? So f of x equals to g of x. So this is the case, right? When x is not 0. And they're the same everywhere else. Well, then this limit, obviously the limit exists. The latter equals to the limit exists, which is equals to -1. We can apply direct substitution, and therefore these two limits is going to be the same according to this theorem. So this theorem is actually very, very important. We use it very often, and sometimes we hardly even notice. So here, I like to bring you guys to the attention to the use of this limit. All right. So this is the limit law. So we have covered these limit laws, right? And in separate topics, I think we're gonna go over maybe just one more example, right? Maybe two more examples. We did example number 1. So we did addition, subtraction, multiplication, division, and all these other cases, right? We did let's look at another example. Example number 2. Okay. Example number 2, we're going to look at the limit, and this is the limit of our interest. The limit as h approaching 0, and we have a quotient. This quotient is 3 plus h squared subtracting 9 divided by h. Okay, we have learned all of these properties, right? Direct substitution, right? Limit laws, and etc., etc. I'm going to box the direct substitution because this is the one we're going to use very often as well. Now, can we use, we have learned all these limit laws, right? Can we apply the limit law? Say, can we apply the quotient law? The quotient, right? So I'm going to bring this over to the top and put it next to the quotient. Can we apply this quotient law of property, law of limit property? Apparently not, right? We have a numerator, we have a denominator. The condition that the denominator, the limit of denominator cannot be 0, even though the limit exists, is 0. It doesn't apply, because to apply the quotient law, we have to guarantee the limit is not 0. The limit of the denominator is not 0. So we cannot apply this one here. So what can we do? So we're going to use our algebraic technique. Okay, so in our algebraic technique, we're going to FOIL. We're going to FOIL the numerator, and 3 plus h squared, that's going to be equals to 9 plus 6h plus h squared. Okay, continue. We will get 9 and 9 reduced. Can we apply quotient law again? The answer is no, we cannot, because we still cannot guarantee the limit of the denominator is not 0. We can't. But what can we do? So we're going to factor out the h, because h is approaching 0, but it is not 0. So we factor out the h. So inside is going to be 6 plus h, the denominator h. Okay, so we are right next to the intuitive definition of limit. You can see that in the definition of limit, right, we don't require the function is defined at 0. And in fact, it is not, right? This function is function of h, is not defined as 0. But that's fine, because we just want h is approaching 0. 0 is not in the domain. The function is not defined there. It's okay. Actually, it's good, because if h is approaching 0 but not 0, we're going to use the fact that h is not 0, and we can simplify the h. We can reduce the h. Then we will end up with 6 plus h after the reduction. Okay, and then we're using this property that we talk about, right? this property. I put it here, right? So 6 plus h, and this function, or all of these functions, they are the same except at 0. And the latter has a limit, and because this can be seen as a polynomial, we can just do direct substitution. So it's going to be 6 plus 0 equals to 6. The limit is found. The limit is found, right? You can see each step of the way, right? We need to be aware of the definition, the intuitive definition of limit. It says x is approaching a, but not a. H is approaching 0, but not 0. Okay, let's look at another example, example number 3. In this example, we're going to look at a limit. This limit is t approaching 0. And we have a quotient again. Okay, we have a square root of t squared plus 9 minus 3 divided by t squared. Once again, can we use the quotient rule? No, the answer is no, because for the same reason, right? We cannot guarantee the limit of denominator equals to 0. So we cannot apply quotient law. And therefore, we're going to do the algebraic methods. Okay, so how do we do it, right? As t approaching 0, this piece is approaching 9. Square root of 9. Square root of 9 is 3. 3 minus 3 is 0. So the top is approaching 0, denominator approaching 0. We have a 0 over 0 case. What can we do? Not much. But even though t is approaching 0, but t is not 0. Okay, we want you to remember that. The intuitive definition of limit is right here. Then what we can do? We can do rationalization. Okay, so we're going to rationalize. We're going to take the conjugate of the numerator and make number 1. So we make number 1. So this is a number 1, right? So this is a 1. When anything times 1 stays the same. So we multiply this 1, and we want to reduce it to see what we get. And apply algebraic technique, right? The numerator times numerator, we have a situation of a plus b times a minus b. Well, you can see it as a minus b times a plus b, same thing, right? And this is equal to a squared, if you FOIL it, minus b squared. Okay, and what applied here in our situation, the a is t squared minus 9, t squared plus 9, and the b is 3, and t squared, a square root of t squared plus 9 plus 3. According to this formula, and this is going to be equals to that minus 3 squared. Minus 3 squared. Okay, so we apply this formula here, and what do we get on the next step? On the next step, we get on the numerator, right, a minus b times a plus b, and that's going to be this piece. Denominator, we keep the denominator, multiply the denominator, multiply the other denominator. Boom. And reduce the numerator. When we reduce the numerator, what do we get? Let's see, what do we get? We have t squared plus 9 and then squared. So this piece equals to just t squared plus 9. Okay, so this piece is just t squared minus plus 9. T squared is 9, right? So this is 9. And the next step we got, oops. The next step we got t squared, 9 minus 9 reduced, and we got a t squared over t squared that can be reduced. Can we reduce that? Well, t is approaching 0, but is not 0. If t is not 0, t squared is not 0. If t squared is not 0, we can reduce them. And by this time, we got this. According to the law of limits, we can do and the direct substitution, right? Because even though this is not a rational, but we can, each individual piece, the limit exists. The limit of the top exists, right? It's constant. The limit of the bottom exists. It is not 0. This time we can apply limit law. We can apply limit law, which is the limit of 1 is 1, and the limit of the denominator, we can apply the quotient law, in fact. So that's going to be equal to 1 over, so this is direct substitution, and that's going to be 0 plus 9, and outside plus 3. And now in the end, we get a 1 over 6. We get 1 over 6. Then you can see limit law applies. And along the way, we have used this property, right? On the latter steps. And we have used some algebraic techniques. And we also use the intuitive definition of limit. What part of intuition definition of limit? Well, x is approaching a. In our case, t is approaching 0, but it is not 0. All right. So those are the definitions of limit. We use definition of limit. We have used the limit laws. All right. So that's all for this lesson. That's all for this lesson. We're gonna have other lessons to cover, other topics. But by this time, how many tools do we have? We have 1, 2, 3, 4, 5, 6, right? Then you say, wait a minute. Does the intuitive definition, does the infinite limit consider limit? The answer is no. In other words, for the laws of limit, for the application of laws of limit, if any one of this limit is infinity, and that doesn't apply. If any one of these limit is infinity, it's considered that does not exist. You cannot apply the laws of limit. Okay, so now we have all of these definitions, theorems, direct substitution, and in the next recording, we're going to be talking about, we're going to use them to apply to more examples. Thank you for watching.